we have our function which we want to differentiate. We want to find the derivative. But not only do we want that, but we want to find the derivative at a particular spot at f or at x equals 3 pi by 2. Here's what I'm going to do. We've got two kinds of functiony things going on here because we've got our sine x, in the main part, and then it's to the power of x. So how I'm going to treat this is I'm going to treat this as a multivariable function, the kind that you would use in calculus 3. I'm going to treat each of these x's separately. And here's how I'm going to do it. I got to find so we'll rewrite this as a function in two variables, x1 and x2. And so that equals sine of x1, okay, plus 1, all to the power of x, the 2 subscript. And we will differentiate this multivariable function. And here's how we'll do that. F prime of x1 comma x2, that's an x of sorts, equals the partial derivative. So we use the del operator, which is a fun to make d, or it's a backwards 6. So first we differentiate with respect to x sub 1, and we treat x2 as if it's a constant. Sine x1 plus 1. So x2 in this partial derivative is a constant. Okay, and then we're going to plus the partial derivative with respect to x sub 2 of sine x sub 1 plus 1 to the power of x2. Okay, so now the bit in parentheses here, we're holding it constant, and we're going to differentiate the exponential. Alrighty. So let's roll with that. So the first part, let's look at this bit right here. We'll scroll, and let's see here. I actually made notes. All right. So this part here, that's going to be take this exponent, which is just a number in this scenario, down here in front, sine x1 plus 1, and then x2 minus 1, because here the x sub 2, it's just a constant number. It could be 4 or 3 or n, but we're differentiating with respect to x1, so now we need to use the chain rule and differentiate what's inside here, and we get the cosine of x sub 1. Okay, done. That part of the partial is done, and then now we'll do this bit. And here, that looks like an N, but that's a really ugly 2. It's a fancy 2. It looks like a bird. Okay, so now we're differentiating with respect to x sub 2. Okay, so now it's going to be an exponential. And how do we deal with that? Well, it's going to be the function itself. That's this part here now that we're dealing with. The function itself to the x2 times the logarithm of this base here, which in this scenario now is just a number. So it's going to be log of sine x to the 1 plus 1. And this is the solution to the derivative when we treat it like x, the two x's are different. We treat it like a multivariable function. Okay, but let's rephrase it in terms of the original question, which was just in terms of x. So now we can go back and just write x's. So here we go. So this means that f prime of x, let's see here, f prime of x is, shut off the banner here now, equals just x times the sine of x plus 1 all to the power of x minus 1 times cosine of x. And then we're going to add that to the logarithm of sine of x plus 1. And I'm going to put what we're multiplying the logarithm by, I'm going to put it up here as an exponent. So that's going to be sine of x plus 1 all to the power of x. Okay, and that's our general derivative. But we want to go a step further, and we want to ask, what is this derivative valued at? I'm bouncing around here. Lost myself. What is this derivative valued at 3 pi by 2? So let's just stick that in. And so we get 3 pi by 2 times the sine of 3 pi by 2 plus 1 all to the 3 pi by 2 minus 1 times cosine of 3 pi by 2. Okay, and the sine of 3 pi by 2 is -1. So this just becomes -1 plus 1 in the parentheses. So we have 0 times 3 pi by 2 times 0 to the power of, just, this is some number, 3 pi by 2 minus 2, 3 pi by 2 minus 1 over 2. Let's just keep it the same way. Let's not try to simplify that any further. Okay, and that's going to be all times the cosine of 3 pi by 2, which is 0. So this first part before the plus sign is just all 0. Okay, now let's go over. So it's going to be 0 plus, and let's give special attention to this baby here. We have got the log of, well, sine, we already did sine of pi by 2 plus 1. That's the log of 0. Sine of pi by 2 times 1 is 0 to the power of, and that was just x up here. So that's 3 pi by 2. So this bit here is just 0. So we've got the log of 0 to the power of 0, which is, yeah. what is 0 to the power of 0? And I posted this to the community tab. We voted on it, and here's what we ended up with. Share screen, Chrome tab, channel content. Is this it here? There it is. So we voted. So far, we've had 84 votes, and 15% say it's 1, and 12% say it's 0, and a whopping 61% undefine it, and then we get a nice response down here from actually 12%. So what is it? We need to go to that bastion of knowledge in the internet, and that is Google. I'm going to show you that now. If I can find it. Da-da-da. Share. Stop screen. Share. Share screen. And Chrome tab. And where is it? There it is. Ta-da! So 0 to the power of 0, according to this piece of wisdom, is 1. But according to these notes over here, it's undefined. So, but the calculator says 1. So what's going on? There is an amazing amount of discussion on 0 to the power of 0. And you can read about it in Wikipedia. And here's the part that I want to show you. There's all sorts of discussions about this. Complex exponents as a value, as a limiting form, current situations. There's, Knuth argues this, and Cauchy says that, and there do not appear to be any authors assigning a value other than 1 when they describe a specific value, but other authors, right here, other authors leave 0 to the power of 0 undefined because it's an indeterminate form, okay? But here's the part that I want to point out. The choice is based on convenience, not on correctness. If we refrain from defining 0 to the power of 0, then certain assertions become unnecessarily awkward, like the solution to my problem here. And the consensus is to use it as 1, although there are textbooks that refrain from defining it. Let's see, here we go. Knuth draws a distinction between the value 0 to the power of 0, which should equal 1, which looks to me like what we've got. We plugged stuff in and we got 0 to the power of 0, and the limiting form, the limit of this. Okay, in which case it's 0. So you know what? We can talk about this, but we won't here. I'm going to leave it to you. I suggest that you, let's just go here. I suggest that you check out the description. I have got the video from Bry, the math guy, who I saw his video and thought, hey, I want to see what I can do with this number. He manages to use first principles in the definition of a derivative to beautifully come up with a value for the derivative at this point, and he gets 0, which is consistent with what I've got here. Hang on here, let me just scoot back over here. Skip it. It's consistent with what I've got, where I have the log of 0 to the power of 0. If we treat that as 1, the log of 0 to the power of 0 is going to be 0, and so the whole thing is 0. But he gets to it a little bit more rigorously. So check out that video, check out the Wikipedia article, check out also in the description. I've got the log of, not the log, the derivative of x to the power of x, so that you can see how I'm the other way that I'm doing that, treating it as a multivariable function. And until next time, cheers. Thank you for watching. Bye-bye.